We're going to use conditional probabilities to investigate quite an important aspect affecting many medical tests. So as I'm sure you're aware, as medical science has improved, people have developed tests to see whether people have diseases which might not be obvious to the naked eye. But no tests are 100% accurate, and there are different ways in which medical tests can fail. So one of the first things to think about is it's a problem if the patient doesn't have the disease, but the test says that they do. This is called a false positive. And as you can imagine, it's not great psychologically for someone to think that they have a disease which they don't have. And it's also not good for them physically if they start receiving treatment for a disease that they don't have. And the costs might also impact on the health sector and things like that. So that's called a false positive. The other thing that could go wrong with a test is if the patient does have the disease, but the test says that they don't. And this situation is called a false negative. And this also obviously has negative repercussions because the person's not going to start receiving the treatment that they need. They might, if it's a disease that can be passed on, pass it on to other people because they don't realize that they have it, things like that. So it's very important to know if a person has a medical test and they get a positive result, what the likelihood is that they actually do have the disease. Obviously, in a perfect world, tests would be perfect and we wouldn't be asking this, but unfortunately, we do need to ask these questions because medical tests are not perfect. So let's think about how we can model the situation. So we're going to start with a particular example. So we're considering a medical test and it's going to just screen for some disease. And the first thing that we know is that this disease is found in 5 people in every 1,000. And what we also know is that the false positive rate is 3% and the false negative rate is 1%. And we'll come back to the rest of the sentence in a moment, but the question that we're asking is, what is the probability that a randomly chosen person who tests positive for the disease actually has the disease? So the way we model this situation is by, I think, initially drawing a diagram that's going to be helpful. So here we have our whole population, our sample space if you like. We're going to call it S. And our sample population is divided into 2 groups. The people who really have the disease, which we're going to call S1, and people who don't have the disease, S2. And ideally, we would know exactly who's in each of these categories, but we don't. Instead, we have to do tests. So we're just going to write down some information that we have here. So we know that S1 are the people who have the disease, and S2 don't have. And we have some information. We know that 5 people in 1,000 have the disease. So we know that the probability of being in S1 is 5 out of 1,000. And since you either have the disease or you don't, we can work out straight away that the probability of being in S2, i.e. not having the disease, must be the complement of PS1, which is 995 over 1,000. Okay. And now we're going to think about a different partition for our data into people who get a positive result and people who get a negative result. So what I'm going to draw here is this partition, which I'm going to call A, is going to be the partition that has people who get positive result. And the remaining partition, which I'm just going to label A complement, is going to be the people who got the negative result. Now let's have a look at the various blocks of people that we've got we've got 4 divisions of our people, and it's worth thinking about what each block represents. So if we consider this first block over here, these are people who both have the disease and got a positive test result. So we call these our true positives. So our true positive, these are the people, so the probability of being there is the probability that you have the disease and your test result says that you do. The next block that we're going to have a look at is the block below the true positives. So these are people who have the disease, but the test said that they didn't. So this is called a false negative. They got a negative result, but they shouldn't have. And our false negative, the probability of being there, in there is the probability that you have the disease, but that the test gives you the wrong result. The next block that we want to have a look at is the top right block. So people here don't have the disease, but the test says that they do. So these are our false positives. And the probability of being in that block is the probability that you don't have the disease, but you get a positive test result. And then finally, in our bottom right corner, these people don't have the disease, and the test says that they don't have the disease. So these are called our true negatives. And the probability of being a true negative is the conditional probability that you don't have the disease and the test says you don't have the disease. So this is the information that we can get out of this diagram, but bear in mind the question we're actually asking is, what is the probability that a randomly chosen person who tests positive for the disease has the disease? So what we want to find out is the probability that a person who tests positive for the disease actually has the disease. And notice that this conditional probability isn't one of the ones that we've mentioned over here. So it isn't something that we can use what we've done so far to compute. We're going to need something else, and that something else is called Bayes' law. But before we get there, let's just see what we can figure out from the data that we've already been given. So we were told that our false positive rate is 3%. So we know that the probability of getting a false positive is 0.03. And we're also told that our false negative rate is 1%. So our false negative is 0.01. So the thing we'd like to know is, can we work out our true positive and our true negative rates? And the way we do this is we look at all the people who have the disease, and they either get a false negative or a true positive. But we know that 1% of them get a false negative, so that means all the rest of them must get a true positive. So we know that our true positive must be 1 minus 0.01, which is 0.99. Similarly, if we want to think about what our true negative is, now we're looking at people who don't have the disease, and our true negative must be 1 minus all the false positives, which is going to give us 0.97. So if we look at these, this gives you a sense of vague accuracy of the test. You really want to have your true positives and your true negatives to be as high as possible. And it's not bad in this test, in this particular test. And you want to keep your false negatives and your false positives as low as possible. So we've figured out pretty much all we can so far. Now we need some way of going from conditional probabilities, which are conditional on having the disease, to conditional probabilities which are conditional on having a particular test result, and then being able to say whether you have the disease or not. So the answer to this question was developed by Thomas Bayes, and initially this theorem might look a bit hairy, so we're going to look at a simpler version, but this is the general version, which you can have a look at later if you're feeling particularly full of energy. So let's just read through what it says. Let S equal to, in our case, we're just going to have S1, S2, be a partition. So our S1 and our S2 are partitioning our sample space. Then it turns out that for any event in our sample space, we can find the probability of that event, the probability of being in one of the particular partitions, for example, let's put S1, given that the event occurs, this is equal to this thing over here, the probability of just straight being in that block in the partition times by the probability of being in that block and getting the result that you want, divided by, and in our two situation case, we repeat what we just had in the numerator, and then we also add the probability of being in the other block of the partition times by the probability of being in the other block and getting the result. So this might all look a little bit complicated. We're not going to do a proof for this, but I recommend that you learn in particular this version. We're unlikely to do a version which has a partition with more blocks than 2. Okay, so now that we've got this, let's see what we can do with our problem. So we're going back to our problem over here. It's exactly the same one we had before. I'm going to just paste Bayes' theorem that we have, and let's also go back and get the information that we worked out. So let's just copy all of this. Okay, so now we have everything that we need. So we can actually just go straight ahead and plug in and see how it works. So we've got the probability that you do actually have the disease, given that you got a positive test result, is going to be equal to, so we've got the probability of having the disease, so we know that that's 5 out of 100,000, times by the probability of getting a positive test result given that you have the disease. So that's our 0.99, and I'm going to write this as 99 out of 100. We have the same first bit in our denominator, and then we have to add the probability that you don't have the disease, so that's 995 out of 1,000 times by the probability that you get a positive result given that you don't actually have the disease. So that's our false positive rate over here, which is 3 out of 100. So you can take a moment and just plug that into your calculator and see what you get. So if you plug this into your calculator, you should have got 0.142 and some other stuff, which is the same as around 14%. And this might come as a bit of a surprise. What this is saying is that if you got a positive test result, then the likelihood that you actually have the disease is only 14%. So what's going on? Because if we have a look at our various true positive, false negative rates, it doesn't seem like that can be very likely. But the thing to think about is that there are only 5 people in 1,000 who actually have the disease. Most people don't have the disease. And so you're going to have a lot more false positives than you are going to have true positives, simply because there are so few people to actually have true positives with, because there are so few people who actually have the disease. So that's really what's going on here. So it took us quite a while to get this all set up, and it's a good idea to practice doing these sorts of problems. So here's another example to work through. Given the following statistics, what is the probability that a woman has breast cancer if she has a positive mammogram result? So I'm just going to add in one little thing here, that a woman over 50 has breast cancer. So what you need to do is draw your little sketch, figure out how you're partitioning the space, and see if you can work out the answer. And when you've done that, come back and check that you got the right answer. Okay, so hopefully you've had a chance to work through this example, and if you check the notes and this bit here, I've done the calculation. Make sure that you understand it, and if you don't, head along to the tutorial or come to my office hours. Okay, so far we've been looking at conditional probability, where the probability of one event happening depends on what's happened previously. But obviously there are situations where this is not the case. For example, if you flip a fair coin, then what happens in your second flip has absolutely no bearing on what happened in your first flip. So we want to have some language for talking about these kinds of events which don't depend on each other at all. And the notation and the vocabulary we use is we say that events which don't affect one another are called independent events. And the way we look at them mathematically is we say that the probability of A and B happening is just the same as the probability of A happening times the probability of B happening. So just to clarify, we've got, this is the probability of A and B happening. And over here we've got the probability of A happening, and we're timesing that by the probability of B happening. But you might be feeling a little bit suspicious, because last week we said that the probability of A intersection B was given by the probability of A times the probability of B conditional on A. So you might be thinking, what's going on? Which of these is it? And the thing that you'll notice over here is that because we've got independent events, our probability of B happening is the same as the probability of B happening if A has already happened. Another way of looking at it is, if A happens, B doesn't care, it still happens. So its probability stays the same. And hence we say that A and B are independent. So, given what we've just seen, if we have independent events A and B, then, as I've just said, the probability of B happening, given that you know A happened, is exactly the same as the probability of B happening without knowing whether A happened or not, and vice versa for A. So A doesn't care about B, and B doesn't care about A and whether it happens or not. So a few things to think about. So we've thought about independence, which says that the probability of A and B happening is just the probability of A happening times the probability of B happening. And we've thought about mutual exclusivity, which says that if A happens, B definitely doesn't, or vice versa. So what does that mean? Well, suppose we have events A and B that are both independent, so this is true, and mutually exclusive, so that this is true, then we can conclude that at least one of them has zero probability. So take a moment to see if you can figure it out. And finally, we can extend this idea of two events being independent to having a whole bunch of events being independent. What we're really just saying, if we write this out slightly more verbosely, is that the probability of event A1 and A2 and keep going all happening is the same as the probability of A1 times the probability of A2, keep going. But this is only if the events are independent. If they're not independent, then we need to do something else. So let's see how we can use this idea of independence in an example. So here we've got a coin, and it's not actually a fair coin. It turns out that the probability of it coming up heads if you flip it is 0.6, whereas the probability of coming up tails is 0.4. So you're more likely to get heads than tails. However, this doesn't mean that you would think that if the coin lands heads or tails on one toss, that's going to affect whether it lands heads or tail on the next toss. It's reasonable to assume that the results of the tosses are independent. So we can ask questions like, what is the probability of obtaining two heads? So as with all probability questions, the first thing to do is think about our sample space. Now remember, our sample space is the set of all possible outcomes to our experiment. And our experiment is tossing the coin twice. So our sample set, our sample space, must contain all the possible combinations of heads and tails that you could get if you toss the coin twice. So we've got heads, heads, tails, tails, heads, tails, tails, heads. Now the previous time we looked at this, we said that it was a fair coin, so you were equally likely to get heads or tails, in which case each of these four things was equally likely. But now, since you know that the coin is loaded, it's going to be more likely that you get, for example, heads, heads, than getting tails, tails. But let's just see how these probabilities work out. So we want to know what is the probability of getting two heads. Well, I'm going to let A be the event that we get heads on the first throw. So we know that our probability for this is 0.6, and I'm going to let B be the event that we get heads on the second throw. And we know that our probability of getting heads on the second throw is exactly the same. It's going to be 0.6. Now, since we know that A and B are independent, our probability of getting heads on the first throw and heads on the second throw is equal to the probability of A times the probability of B, which is 0.6 times 0.6, which is 0.36. You'll notice that I said this is the probability of A and B happening. Does this make sense? Well, if you think about our two events, we've got A happening and B happening. We want to find out when both of them happen, so we're looking for the probability of the intersection. So that's just a little reminder. Okay, let's have a look at what is the probability of obtaining one head. Well, let's sketch a tree diagram. So we throw the coin once, and we have a probability of 0.6 that that's going to come up heads, and 0.4 that we're going to get tails. And then we throw again, and again 0.6 for coming up with heads, 0.4 for tails, 0.6 for heads, 0.4 for tails. And so if we look, we can fill in our final outcomes. Following along the top branches gives us heads, heads. Next branch is heads, tails, tails, heads, and tails, tails. And since our throws are independent, we can just multiply the probabilities together. So this is the probability of getting heads times the probability of getting heads, which is 0.36. So our probability of heads, heads, which we actually just proved previously in a slightly different way, is 0.36. Getting heads, tails, 0.6 times 0.4, which is 0.24. So our probability of getting heads, tails is 0.24. We would expect the tails, heads should be the same. Let's just check. Well, that's going to be 0.4 times 0.6, which is also 0.24. And finally, the probability of getting tails on the first throw and tails on the second throw is going to be 0.16. But the question is actually asking us, we want the probability of one head. So this needs to be the probability of all the outcomes where we have exactly one head. So it's this one and this one. So it's the probability of the event heads, tails, union the probability of tails, heads. And here we're thinking of this union as OR. So if we get heads, tails, or tails, heads, then we get exactly one head. And this is just going to be, if you go back to our earlier probability rule, the probability of heads, tails, plus the probability of tails, heads, which is 0.48. Okay, so our next question is asking what is the probability of obtaining no heads? And there are different ways you could do this, but the easiest way is to just say, well, the probability of no heads must be equal to the probability of getting both throws giving a tail. So that must be, if we read off from here, 0.16. And then the final question says, what is the probability of at least one head? So note the at least. And this, you could go through and you could say, well, okay, we've got to add up our probability of heads, heads, and probability of heads, tails, and probability of tail, heads, and you could add those up. But another way of saying that is, well, it must be 1 minus the probability of getting no heads, which we saw in the previous question was just tails, tails. So this is 1 minus 0.16, and our final probability is 84. Okay, so we've worked through quite a few things in this section. We've looked at Bayes' theorem and also independent events. So I recommend taking some time to do some examples and just make sure you're feeling comfortable with it before heading on to the next new section.